live now, right? It's going. Hopefully everything's working. So this is called combinations and composition of functions. We're just going to cover 2 sections in chapter 1. And then, like I said, we're going to do today 1.5, Tuesday 1.6. Block day will be like a review day with some things on the packet and a review assignment. And Friday we're going to have a little quiz over these 2 sections and the packet. Okay, there won't be anything too horrible from the packet. So these are some rules for composition of functions. Compositions of functions are when you take 2 different functions and you add them together, subtract them, multiply them, or divide them. Have you seen this before? Yeah. So basically, you just some examples. Some examples that I have is so if I knew this was what happened. Here we go. We're getting back there. Now I can write. Can I write on there? There we go. Okay. So if I have that, for example, if f of x is equal to x squared plus 2x, x squared plus 2x, and g of x is equal to 2x plus 1, 2x plus 1, then you guys could find f plus g of, so this means f plus g of x means just take those 2 functions and add them together, right? So what's f plus g of x? Combine the like terms. What do you get? You have 1x squared, and how many x's do I have altogether? 4x plus 1. That's it. Easy enough? All right, you've done that before. F minus g of x. F minus g, of x. I'm not used to using my multiboard. You just subtract, but in this case, you remember you have to be careful that you have to subtract the whole thing, okay? X squared plus 2x minus 2x plus 1, x squared, so you get x squared. 2x minus 2x gives you how many x? 0 minus 1. So that would be that, right? And multiplication works the same way. You would just multiply this times this. And division works the same way, but g cannot be equal to 0 because then the quotient, the division thing would be undefined. Yes? Easy enough? I need to do an example, multiply and divide. I'm not going to, okay? But I want to talk about that thing about the domain, because that's the thing that always gets people confused. 2 functions with overlapping domains. So, like with this, can I plug any number in there and get out an answer? Yeah, right? So I'm always going to get out, I can plug in any number for x, but where you have to be careful is when you have fractions or square roots and things like that. So I think that's my next slide. Let me see. The composition of the function with g is f of, oh, not there yet, sorry. Okay. F times g of x. Yeah, I want to look at something. Don't write that down yet, okay? I got to go back. I could just open a new page here. So say I were to have something like f of x is equal to the square root of x plus 1. X plus 1. And g of x is equal to x. G of x is equal to x. And I say find f times g. This is not dot, this is times. F times g of x and its domain. Okay? So domain is x values. You guys remember that? Okay? And so f times g of x is just going to look like this times this, right? X times the square root of x plus 1. Okay? That's f times g of x, which could also be written as f of x times g of x. Who can tell me what the domain is? Is it good? Anyone? Yes. Oh, someone's got their hand up. Yes. Avery.
Is it all real numbers?
It's not all real numbers. Yes. Jerens.
Is it
Here.
-1 to infinity?
Is it what? What?
-1?
Yes, it's -1 to infinity. Okay? Because whenever you see a square root thing, they're really easy way. People get really confused by square roots. Okay? Just what I always do whenever I see a square root thing, I say this thing has to be greater than or equal to 0, right? Or, because you can't take the square root of a negative number. You can take the square root of 0. So just set it up like this. X plus 1 is greater than or equal to 0. X is greater than or equal to -1. That's it. Okay? Questions? Easy enough? What if I did G? What if I did G? I'll do G of X times, I'm going to do it like this, a little different notation, but it means the same thing. F of X like this. This is equal to, what's G? G times, oh, it's the same thing, isn't it?
Yeah.
Never mind. The multiplication is commutative, so I was thinking with composite functions. Okay? So we're done. Same, we'll write same. All right. So now we're going to talk about compositions of functions. Okay? And a composition of functions is when you take one function and plug it into another function, right? Kind of like, there's some real life, someone always asks me real life examples of things. Like, how much gas you put in your car is a function of what? Function of how what? How much if you maybe go to the gas station, right? I got to fill up my car with gas, right? So you have $20 in your pocket, right? Got $20 in your pocket. Okay, you got $20. You got $20 in your pocket. You know that song? Okay. Is that what he says? $20? I don't know. Okay. So you got $20 in your pocket. You got to buy some gas, right? So the amount of gas you could buy is a function of, or the amount of money you have is a function of how much gas you could buy, right? How much gas you could buy is a function of how far you could go in your car, right? So that's an example of a composite function. So I have $20, I can only make it to so far, right? Even though it's dependent on the gas, which is, and how far you go depends on how much gas you get. So that's kind of a real life example. So that's what this means. It's like, we'll talk about the domain in a second, okay? But the domain, to find the domain of a composite function, you have to find the domain of this, and what you plug into this function has to work in G. I'll show you what I'm talking about right now, okay? So, and the example you use, or the notation that you use for composite functions is, here we go. Use this notation right here. This means f, if you see this little open circle that looks kind of like a multiplication sign, but not really. This means f of g of x, meaning g, you take g and you plug it into f. This means g of f of x, means you take f of x and you plug it in there. So f of g of x says you take this and you put it into here for x, right? That's f of g of x, which looks like the square root of negative 2x plus 2. That's f of g of x. right? How do I find the domain? Yes, sorry. I'll know your names pretty soon. Logan.
Yeah, you just set the inside of the square root equal to 0.
Right. So not equal to.
Or greater than or
Greater than or equal to 0. Okay. Greater than or equal to 0. I solve this. Okay. Whoops. Equals 0. Solve this, and I get minus 2x. That goes away, right? Greater than or equal to negative 2. Then what? Then what?
Divide negative 2.
Divide by negative 2, and what happens to the...
It flips.
It flips, that's right. Whenever you divide or multiply by a negative, that inequality sign changes. So you get x is less than or equal to 1. Okay? And people get very confused by this domain question, but that's basically how you do it. Okay? Same thing if you have something in the denominator, and denominator cannot be equal to 0, right? So if you're looking for the domain of a fraction or rational function where you have a function in the bottom, then you set the bottom. So x is got to be less than or equal to 1. See if that makes sense, right? What's a number that's less than 1?
0.
0. So if I plug in 0 into here, do I get a positive number that I can take the square root of, right? See, if I took something that was bigger than 1, what's bigger than 1? 2, right? Negative 2 times 2 gives you negative 4. I'd be trying to take the square root of a negative number. See? Okay, so that doesn't work. So that's f of g. G of f is going to look like negative 2. G of f is I take this and I plug that into there, right? So now I have negative 2 square root of x plus 2, right? And then what's the domain of that? You could probably just look at that one and tell me what the domain of that is. What's the domain of that one? Yep, x plus 2, right? X plus 2 has got to be greater than or equal to 0. So x has got to be greater than or equal to negative 2, right? Or like you said, you can write it like this also, negative 2 up to sideways 8, right? Like that. Right? That means, right, square bracket means it includes the endpoint. Open bracket means it doesn't include the endpoint. Yeah? No? Okay, what else do we got here? Is that it? F of g of 1. Oh, we have some cool ones. F of g of 1. Whoops. Going backwards. Okay? Who can tell me what is f of g of 1? What's f of g of 1? Is it 0? Negative 2. It's 0. Who said 0? Very good. Sabrina. You don't get it?
No.
F of g of 1 says take 1, plug it into the function g, right? And take that answer and plug it into this function, right? So f of g of 1 means negative 2 times 1. Get out that answer, which is negative 2. Take that answer and plug it into the square root of x plus 2, right? And if I plug in negative 2 in there, I get out 0, right? Easy enough? Can I go on? We're done? Okay. So this is going backwards, okay? Where they want you to break this apart. I don't like red. Makes me angry. We're going to change colors. Let's change color. So this is just kind of going backwards. Find two functions, h of x, such that h of x is equal to g of f of x. So there's more than one way to do this, but what might I call g of x? What would be, and we call this like the outside function. What could I call g of x if I want to plug in something into something else? Yep, you could call g of x square root of x. If g of x is square root of x, what would f of x be? what would I plug in there to get this expression? What would I plug in for x to get this expression? Yes,
X squared minus 1.
x squared minus 1. Okay? There's more ways than one to do this problem, right? I could have called g of x. What if I called g of x? Is there more ways than one to do this problem? If I call f of x, nah, that doesn't. Yeah, I could have called. This would be kind of not really great, but if I call g of x square root of x minus 1, then what would have f of x been? What would have f of x been? X squared, right? Because I could take this and plug it in here and get that expression. I could take this and plug it in here. So there's more than one way, okay? And when you guys take calculus, there's something called the chain rule. That's very important that you have to take the derivative of the outside function and then the derivative of the inside function. And so this stuff becomes really important when you get to calculus. Okay, move on. Now we get to do the fun one. This is my favorite one. Okay, I like this one. This one. Okay, so this is cool because it's more like conceptual understanding. So this is function g, okay, and this is function f, and they say find f of g of 1. And you say, how can I tell that just by looking at the graph? Anyone have any ideas how I do that? F of g. Okay, so here's the graph of g. G of 1 is really the y value when I plug in 1 in for x into the g function. So what is g of 1? Here's g. What's the y value when I look at this graph? 1, right? Do you understand that? G of 1, if I come over here to 1 on the x-axis, I go up here on the function g, its y value is 1. Then I take that y value, 1, and I plug it into the f function. What do I get out? When I plug in 1 into this function, what do I get out? 3. You understand that? It's kind of tricky conceptually, okay? This is 3. These are the kind of fun questions that I like. F of g of 1. Who can tell me what g of f of 1 is? Who's in the same? G of f of 1. Is it 5? Is it 5?
4 or 5, I guess.
Yeah, it's 4. It's whatever is over here, right? Do you guys see how we got that? Okay. So f of 1, f, where's f? Here's f, right? F of 1 is 1. So then I have to take f of 1, which is 1, and plug it into g, which is f of 1, sorry, is not 1. This is f, right? Here's f, right? Here's g. So f of 1 is 3. So g of 1, 2, 3 is, looks like 4. So looks like about 4. How about f of g of negative 4? Who got that?
3.
Measure g of negative 4. Looks like 3, right?
Yeah.
It's about 3, yeah. Okay, so g of negative 4, you follow the g function until you get to negative 4. You go, oh, what's the y value there? It's 1, right? So this is negative 4, comma 1. Take that 1 and plug it into the f function, and you get out 3. Okay? Those are fun. Fun! Aren't those fun? And I think that's all she wrote. Is that it? Oh. I guess it's not off. I was hopeful. The weekly cost C to manufacture widgets given by 25,000 X plus 5,000. The number of widgets X produced in T hours given by X of T is equal to 3T. Find and interpret C of X of T. So if this is C of X, and I know X of T is 3T, all I do is I take this and I plug this in to here. Okay? And so then you get C of X of T is equal to 25 times 3T plus 5,000. And I could simplify that to 75T plus 5,000. Okay? Can anyone interpret what that means? If I were like in a business, it's kind of like the gas example that I gave you at the gas station, or how many dollars a minute. What is T? How many hours, right? So T might be how many hours you have for production, okay? So if you have so many hours for production, what does C tell you? The cost of producing so many widgets, right, in that amount of hours. Okay, that's what that would be. There's a cost. You don't know how many widgets, you'd have to plug into the widget formula to figure out the cost, how many widgets you get, right? But the cost of manufactured widgets is, or you'd have to know, you could plug in, right? If you have like 10 hours, you could figure out how many widgets you'd have, right? You'd get 30 widgets, and then you could plug into here. Or you could just say, I have 10 hours, this is how much it's going to cost me to produce widgets given that amount of hours. And I believe that's all she wrote. There you go. Okay? So it looks only 1 through 6, 7 through 55, every third. You know what I mean by every third? 7, 8, 9, 10. So it'll be 7. On my Schoology, it's spelled out more precisely for you. But these aren't bad. It's just plugging in. So you go 7, 10, 1 through 6. 1 through 6 are just kind of definition problems. 13, 16, until you get to 55. Okay? So that's it. Okay? And I'm going to pause.